Greetings, everyone. Time to talk about solving linear equations. It's a good place to start college algebra, sort of brush up on any skills that you might be rusty on. This is probably something that you've seen a lot before this course, but nonetheless, let's iron out any kinks, right? So, linear. Whenever you see that word, whether it's in algebra or calculus or wherever, the word always gives the same meaning, and it's supposed to give you the feeling of simplicity. Not in a way of, oh, it's too simple. More like first steps, first things to talk about. Let's get structure out of the way type of stuff, okay? And of course, when you see linear, you think line, but that's not always true. It depends on how many variables you're dealing with, how many dimensions you're dealing in. Linear does, however, always imply that your exponents are going to be 1 everywhere in your equation. So x to the 1, y to the 1, z to the 1. Everything that to the 1 power like that implies linear. Okay? So, next thing to talk about, the golden rule for solving. You've probably heard this all throughout every math course. Whatever you do to one side, you got to do to the other. I also like to add in this extra little tidbit. You can do whatever you want as long as you do it equally to both sides. Okay? Now, of course, some things you do may not help your cause, but you can actually do whatever you want as long as it doesn't cause division by 0 or anything else illegal that you may want to avoid. Any big no-nos. For the most part, whatever you want. For example, I have this equation right here. I can see that it's linear. X is to the 1 power, x is to the 1 power, right? That doesn't matter for the golden rule, but just pointing out, okay? I can do whatever I want. For example, if I really, really wanted to, I could multiply both sides of this equation by 6. Like so. That would result in 18x plus 30 equals 60 and 54, 114 minus 6x. Completely legal, right? As long as I did it equally to both sides. No problem with doing that. Did it help my cause? No, it made my numbers bigger. You could do the same thing with addition, subtraction, division, whatever, exponents. You as long as you do it to both sides equally, okay? That doesn't mean that everything you want to do is going to help towards your goal, okay? So let's start over on this one. Let's take a look at what we actually have before we decide what it is we actually want to do to both sides. Right? Now, this being linear, of course, like I said, implies that simplicity mode, which in linear, it gives you that because all of my variables being to the 1 power means there's no variety. It means all of my variables are quote-unquote like terms, as you've heard before, meaning I can just combine them all together, right? So in this case right here, I have the 3x, I have the single x over here. If they happen to be on the same side of the equation, I could actually combine them. They're not on the same side of the equation, so I can't, okay? Now, sometimes algebra teachers like to throw out there, let's move it over. You need to get away from thinking of things like that, okay? I'm not actually moving anything when I do these steps. Think of it more like I have certain pieces that are in the way of me solving, and I'm getting rid of them. For example, I really don't want my x on the right side in this case, okay? I prefer actually letters to the left, double L's, letter to the left. Not 100% of the cases work like that, but it is a good thing to live by, especially later on when we get to inequalities, okay? So most of the time you'll notice I do go letters to the left. In this case, I'm going to want to add x. And the reason is not for moving purposes. Don't think of it like moving. Okay? The reason is because this x is not in a spot that helps me solve. He's on the wrong side of the equation. So my actual action here is to eliminate this. And since it was a subtraction of an x, I used addition to eliminate it, right? Okay, so now I've got 4x on this side as a consequence. Not because I moved this x over, but because whatever I do to one side, I have to do to both sides equally, right? That's your golden rule in action right there. And this time it actually moved us in a direction that's going to help us out. So I still have the 5 and the 19 here. Again, I have something that's in my way of solving. The 5 is on the incorrect side of the equation for what I want, right? I want just letters on one side, okay? So in this case, I'm going to subtract 5 from both sides. Again, not because I'm moving, because I want to get rid of this 5. That's going to leave me with 4x is equal to 14. Okay? So then you need to think about what's left. Here's where the not thinking of it like moving comes in handy. I'm not moving anything. I want x by itself. That's my goal. So I need to get rid of the 4. Okay, well this time it's not addition or subtraction. It's using multiplication. So I need to do the opposite of that, right? I'm going to divide both sides by 4. Because 4 over 4 gives me 1. And that's actually what we're looking for, 1x. Okay, and then on this side, I'm going to have either a fraction or a decimal. In my classes, I always prefer fraction, even if it's improper. In this case, we reduce it to 7 over 2. You could also say 7 over 2 is equal to 3.5. But like I said, personally, in all of the classes I teach, I prefer the improper fraction. And actually, a lot of the online math homework softwares prefer that as well. Fractions are much easier to type in if the decimal is something that's either repeating or just really, really long. Fractions are going to be eventually easier. But also at the same time, mixed number form doesn't work well with algebra because you have a number portion and a fraction portion that look like multiplication and it's actually not. So mixed numbers don't work well either. The format preferred is improper fraction. Okay, so let's step it up a little bit. Here's another example. Notice it is a linear equation. I have x to the 1, x to the 1, x to the 1. Okay? All of my x's are to the 1 power. But I've got a lot more pieces going on, and I've got grouping symbols, the parentheses, right? So we need to dig way back into our toolbox and remember, hey, what's one way that I can get rid of parentheses if I can't actually work them? Because notice you can't work them, right? 3 and x are not like terms. Those don't have a way of being combined in that fashion. So instead, we want to get rid of parentheses, right? Using our distributive property. The distributive property comes in a few different forms. This is the distributive property of multiplication across addition. So what I'll be doing is not actually changing either side as far as total value, but I'll be multiplying each thing into the parentheses. So -5, don't forget the negative is actually attached to the 5 here. I know it looks like minus, but in algebra we prefer to think of them as attached negatives. So -5 times x, -5 times -3. And then over here, I've got the 3 times 2x and the 3 times -4. And that's going to be using the distributive property. Okay, so then I've got 2x minus 5x plus 15 is equal to 7 plus 6x minus 12. And at this point, if you've got more than two terms on any side of a linear equation, you're going to have to realize that some of those have to be like terms because I'm only doing a linear equation with one variable, right? Since it's a linear equation with one variable, you can only have two types. You can either have with the variable or without the variable, right? If I had more than one variable, then you can have some variety a little bit, but in this case not, because we only have that one variable, okay? So then notice, since I have three terms instead of two, I am noticing that I have some terms that can be combined. And over here, the same thing, right? The 7 and the negative 12. I have more than two terms, so I do have some things that can be combined. So that's what I'm going to do. 2x minus 5x is negative 3x. And 7 minus 12 is negative 5. Okay? So then at this point, I'm back where I was in this original equation over here. I've got a letter and a number on each side, and that's sort of your kickoff point for doing some golden rule stuff. I need to start changing the sides' total values up, and I can do whatever I want as long as I do it to both sides equally, right? Well, remember, we prefer letters to the left, so let's start there. Since the 6x is on the right, he should not be on the right. I'm going to get rid of 6x by subtracting, or if you want to say plus a negative 6x, either way. And of course, if I do that to one side, I'm going to do it to this other side, like so. And also at the same time, and save myself a little space here, I know that the 15 should not be on the left-hand side, because again, letters on the left is the mode that I'm going with here. So I'm going to subtract the 15, which is going to cause me to subtract it on both sides. And remember, the goal here was to get rid of the pieces that were in the way. And that's actually what's happening here, right? These two are going to add to 0. These two are going to add to 0. So they're effectively gone. They're eliminated. Okay? So then that leaves me with negative 9x equals to negative 20. So then I just have the one thing to get off of the x and get away from the x. And so I'm going to divide by negative 9. Right? So x is negative over negative, right? Two negatives in division is positive. 20/9 does not reduce. So I'll leave it as 20/9. And as I said in the last problem, improper fraction is preferred. If you did want to actually divide this out, you would get a decimal of 2.22222. And then, of course, we also have the shorthand for that. 2 with a line over it like that. And again, this is why we typically prefer the improper, right? A much more concise way, and also not having to chop off any value. It's definitely possible to have any type of number in the equations that you're solving. So let's start by talking about decimals. It's completely possible to have decimals. It doesn't make the equations ugly in any kind of way, nor does it make them any more difficult. It's just something else that you have to consider. And I want to show you two different methods that we typically approach these with. Okay? The first one, just flat out straightforward, right? I go straight for the way that we were just doing before. I'm looking at this being a linear equation, right? X to the 1, x to the 1. I can see that. Then I decide, oh look, there's two terms on each side, no like terms on any individual side. I can't combine anything here or there. So then I start with my letters on the left mentality, and I'm going to get rid of the things that are in the way. So in this case, I don't want this letter here, so I'm going to subtract 0.2x. So that piece will eliminate right here. Next, I also don't want the 13.2 on the left-hand side. So again, I will subtract because it was positive, and that eliminates this one. But then, of course, I have to do it to both sides, minus 13.2 here. Okay, so 0.5x minus 0.2x, I just make sure all of my things are lined up in my mind to do the subtraction. And that leaves me a 0.3x. And then over here I've got 9 minus 13.2. And if it helps you, just do your subtraction, out here. I'm doing 13 minus 9, I know, because what's going to happen is I'm going to end up with a negative number here. But really what I'm doing is just subtracting the sizes, right? So I've got 2 minus 0, which is 2. And then I've got 13 minus 9, which is 4. So I've actually got negative 4.2 here. And then, like before, I've got something where I've got the number x, the number times x on one side, and then the number on the other side. So then I'm going to divide both sides by whatever's multiplied by x. Okay? So then, of course, 0.3 over 0.3 is 1. That's why we go for that. It's just a solid 1x. Notice whenever I do these divisions, by the way, that I'm not dividing by x. That's a common mistake I see a lot of. Do not divide by x here, right? That's going to put x in your denominator over here and just get rid of it over here. You don't want that. I only want to get rid of the number portion. Okay, so then I've just got to do this division right here. I've got to do 0.3 into 4.2. And of course, negative divided by positive is going to give me a negative answer, right? And of course, you've got your old school version of division here. You can move your decimals. And it's really just 3 into 42, right? 3 goes into 36 12 times. So let's count it up, right? 39, then 42 would be 14 times. It actually goes evenly. So I'm getting negative 14 here for this. All right. So then an alternate version over here that every once in a while you may want to use or you may not. With decimals, it's not so bad to go straight forward because they act a lot like our traditional numbers. You just line them up the same way with different place values. But if it really does bother you to have the decimals in the equation, you just want to get rid of them, okay? Well, one quick step can do that for you, and that is to notice how many decimal places you have and to call out that lowest decimal place. In this case, I notice I have one decimal place, and 3 of them, and that's the lowest. If it had been 2 or 3 or 4 in one of them, then I would find that lowest one, okay? In this case, it's just one decimal place. And think about the name of that decimal place. The first decimal place is the tenths, right? That means it's 13 and 2/10. Okay? Well, that's a hint. If I multiply by the name of that decimal place, tenths, hundredths, thousandths, whatever, then you actually get that many decimal place movements from your multiplication. For example, here it's tenths. So if I multiply times 10, then 10 times 13.2 is going to give me 132. Okay? So here's what I'll do. I'll multiply the 10 times the whole side, which of course if I'm doing it to one side, I have to do it equally to both. Just because you want to, right? You can do it just because you want to, and as long as I do it equally to both sides. So I'm doing times 10 here. That'll give me 132. And 10 times 0.5 will give me 5, x in this case. Then 10 times 9 is 90. And 10 times 0.2 is 2. So like I was saying, if the decimals really do, irk you, or you just don't want to have them in the equation, it's completely okay to multiply by some round number of 10,000, 100, whatever, and it'll move the decimal for you, right? And then, of course, the actual solving is no different here. It'll still look a lot like this one because none of the numbers actually change. It just move the value of the decimal point, right? So again, I like my letters on the left, so I'll be subtracting the 2 here to get rid of that one. And I'll be subtracting the 132 from the left-hand side to eliminate that one. Okay, so then my equation here is going to eliminate these, and I'll end up with 3x is equal to negative 42. And I'll want to divide by 3. Notice that's the same division we ended up doing with our division, right? Because with division, you end up matching the decimal places anyway, right? 42 divided by 3. I still get the negative 14 that we got before. And it needs to be that way, right? There's only one solution to this equation. Okay. Of course, the other variety of numbers that can land in your equations is fractions. And I know that's the naughty F word of mathematics, or one of the many. Fractions, fractions, fractions. Say it real quick. Get your mind used to it. We have to be able to deal with these. Okay? So the approach is going to be kind of like the last thing that I just showed you with the decimals. I can do whatever I want to both sides as long as I do it equally. Okay? And yeah, you need to look at these fractions for what they are, right? Fractions are actually created, they're developed with division. So if I use multiplication, I can actually make the denominators go away. And then that would be something that's a non-fractional equation, okay? And later on in the rational solving and equation section, that's going to be a paramount step. So let's start by practicing it now. I see in this problem that I have some denominators of 7 and some denominators of 5. I need one multiplication because I have to do it to both sides equally. I need one multiplication that can eliminate with a 7 or a 5 through multiplication and division. And that's where the old LCD comes in, right? Lowest common denominator. What is a number that both 5 and 7 can multiply into? And typically, the easiest thing to do is to just multiply them together, but it's not always true, okay? So in this case, 5 and 7 both being prime numbers, 5 times 7 is going to be the best way to go, 35. So what am I going to do? I'm actually going to multiply by 35. Okay, and what's going to happen is I'm going to multiply it to both sides equally. Right? I'm going to end up multiplying it to both sides equally. And since it's multiplied by the whole side, it gets distributed. So I'll have also a times 35 here and a times 35 here. When it comes to these, I go ahead and write it out so that we can see all of the steps that are going on here. And what you want to do is simplify the fraction first with the division before you do the multiplication. Because you can do it in either order. I could do the 35 times 12 first. That's a big multiplication. It would be much simpler for me to do 35 divided by 7 first. That's going to come out to be a whole number because I specifically picked 35 to do that job. 35 divided by 7 is 5. then times the 12x. So that will result in 60x. Okay? Then 35 divided by 5 is 7 times 3 is 21. 35 divided by 7 is 5 times 9 is 45. Minus 35 divided by 5 is 7 times 11 is 77 times x. Real quick, notice I did actually write these two different ways on purpose. I have the x in the numerator here, and I have it outside here. I want you to notice that those are actually the same thing, as long as the x is not in the denominator, okay? The x being in the numerator and the x being out to the side are equivalent. And notice they did have similar results, just different numbers, right? Okay, so now we're in a linear equation, right? Still x to the ones, but no fractions. So I can attack it the way we've been attacking it. I say letters to the left, so I don't want this guy here, right? So I'm going to add 77x, because that's what will eliminate with negative 77x. So I'm going to add 77x. All right. Also, I don't want the 21 on this side, right? I want those things all on that side. So I'm going to eliminate with a minus 21. Resulting in 137x. Over here, this eliminates. So 45 minus 21, 24. Okay. And then, of course, I'm going to want to divide both sides by whatever it takes to get rid of this number here. Since this is multiplied, I'm going to divide by 137. So I have 24 divided by 137. And then we just check and see, can I reduce this at all? Well, let's see. 24 can be divided by 2, 3, 4, 6, 8, 12. 137 is not an even number, so it can't be divided by 2 or any multiple of 2, like 6 or 12 or 4, right? So we can count those out. Also, if I add the digits up, 1 plus 3 plus 7 is 11, which is not divisible by 3, which means 137 is not divisible by 3. Okay, so they don't have any common factors. Even if 137 does happen to have something in it, they don't have any common factors. Okay, so then this is where I'll stop. Okay. Next example, dealing with the fractions still. It doesn't matter how complicated your numerators are. I can approach it the exact same way, all right? So I'm noticing the 9, the 6, and the 18 first, because those are the denominators I want to get rid of. Well, what's a number that 9, 6, and 18 can both multiply into? Well, that would be, in this case, don't multiply the 9 and the 6. It would work. It would give you a much bigger number, right? 54, and then you'd have to see, does 18 go into 54? Well, of course it does, right? But no. 18 is the number you're looking for now, right? 9 can multiply into 18. 6 can multiply into 18. 18 times 1 is 18. So that's the guy I'm looking for. I'm going to multiply by 18 here. It's going to get distributed on each side. So times 18 here, times 18 here, and times 18 here. Remember, do the division first. 18 divided by 9 is 2. And I'm going to write out this step here. The 2 is multiplied by the entire numerator. Okay? I'm not just going to do 2x. Don't make that mistake. The 2 is times the whole fraction. Or, well, in this case, the whole numerator, because after you get the 2, the denominator is 1. So this is what's left over. Now that I'm doing single ones on all these other ones, I can just simplify. 18 divided by 6 is 3. 18 divided by 18 is 1, so 1x. And then no division here, just 1 times 18. We're almost to the normal linear, right? I just need to distribute my 2 now. So 2 times x, 2 times 4, 2x plus 8 plus 3 equals x plus 18. And then, of course, I have more than 2 terms on this side, so I know that I'm going to have a couple of them that will combine. 2x plus 11 is equal to x plus 18. Quick question. Did I absolutely have to do this step? The answer is no. If you really just missed it, that's okay. But you are eventually going to have to get rid of the 8 and the 3 anyway, right? Because they're on the wrong side. Just like right here, the 11 is on the wrong side. I want letters on the left. So you would end up having to eliminate the 8 and the 3 separately, which would just give you 2 subtractions over here that would add up to the same kind of subtraction that I'm about to do here. Either way, I have to subtract a total of 11. We just find it easier to look at when those two are consolidated. Okay? And of course, also, I have this x to get rid of, because that shouldn't be on that side. So I balance it on this side with a minus x also. So then I've got a total of x, and 18 minus 11 is 7. Okay. Let's finish up this lecture by talking about a couple of special cases that can happen. And these aren't very common, but you do need to know that they exist, and you need to know how to treat them and how to express the solutions that come up. Okay, so I've got this equation here, and I'm going to solve it the normal way. But one thing you're going to notice is going to happen is my variables are going to completely eliminate from the equation altogether. Okay, and when that happens, you only have 2 situations, and that's why I've got 2 examples. Okay, so let's look. I'm going to use the distributive property here. I'm going to combine the 3x and the minus 8x to give me negative 5x plus 10. And then I'm in my situation where I want to have all my letters on the left. Okay, so in doing so, I am getting rid of the 5x that's on this side. And in this case, that means I have to balance it by adding the 5x over here. But then what actually happens is I get the elimination on this side also. So the only thing that's left is 10 equals 3, which is false. Okay? Now, I know we haven't talked about solutions much yet, because I haven't. We're going to talk about that a lot more when we get into inequalities. But what a solution means is something that causes your equation to be true. Okay, if you go back through the equations that we've talked about, most teachers would have you quote unquote check your solution by plugging it back in. All you're doing is making it act like a solution, which is something that causes a true statement. Okay, in this case, I'm not getting a solution because this was already false. Okay, whenever you're doing these steps, you're doing equivalent equations here. So if this one is false, that means this one was false, this one was false, this one was false already. There's no way to make it true. So there's no value of x that could make this original statement a true statement. So then you have to put no solution. Okay, so this is the situation. Whenever your variables completely wipe out and you get a false result, right? 10 does obviously not equal 3. Then you're going to have no solution in that case. Over here on this other one, it's the other situation. Watch. I'll use the distributive property. So I had to distribute -1 here. -1 times x is -x. -1 times -4 is +4. 5 plus 4 is 9. And you should already be able to see it. The two sides are identical, right? The next step that I would do here is I want letters on the left. So I would add to eliminate this one. But in doing that, I actually eliminate both of them. So it's just like before. All of my variables vanish from the existence of this equation. However, the statement that I result with this time is completely true. Right? That means the statement before it was true, the statement before that was true, and so on and so on. Which means it was always true. It didn't need x to become true in that sense. Whereas this one was always false, and all of the equations we've been doing this whole lecture are conditionally true or false. Conditionally meaning I could take that one value and plug it back in and make it true. This one is always true. So that means it doesn't matter what I put in for x. This statement would always be true. So in this case, you can say that x is any number. We'll say any real number. Although technically we could say x is any number. We're going to talk about other number systems, and in this case, x literally could have been anything. So x is any real number, okay? Later on, I'll show you some symbols, but let's go ahead and let me just introduce them real quick. If you write that in Mathese, it would look like this. Or like this. Okay? All three of those statements say the same thing. Pretty soon we'll talk about interval notation, so you'll understand that one. And this double line R is the symbol that we'll be using for our real number system, every number that's on the number line. Okay? So these are just some symbolic ways that you may also see that displayed. But this is what's happening. If you end up with a completely true statement, then you have to say that X could have been anything because the thing was already true. And that's our goal in solving, is finding out values that make equations true. And we call those solutions. Okay, so I hope this has helped you brush up or learn or whatever along your endeavor for solving linear equations.